All right, we are recording. So we are talking about section 10.2, derivatives and integrals of vector functions. And in our last class, we certainly talked about the derivatives of vector functions. And we looked at multiple examples. And I want to do a warm up on one of the problems that was in your homework. I just want to make sure you're comfortable with this particular problem. So let me give you a moment to copy it down. And then after we do this problem, we're going to talk about integrals of vector functions. So let me give you a moment to copy this example down, and we will proceed to the solution. Okay, so hopefully you have it copied well by now. So, all right, you're given here two space curves, R1 and R2, R1 and R2, two position vectors that trace out two space curves in space. And you notice that these two position vectors, R1 and R2, you notice too that they're independent of each other because the parameters are independent. Okay, so we want to find, well, we want to know at what point do the curves intersect. Now, if they're saying at what point do the curves intersect, that means these curves do intersect. And where the curves intersect, they'd have to pass, at the intersection point, both curves are at the same point. Okay, so when you look at this problem, it might seem a little intimidating, but you just have to sort of think through what needs to be done. If these are like two missiles, okay, think of like, Israel, the Iron Dome, if it's intercepting a missile coming in, or any other situation, okay, or vice versa, whatever. But if you have one, I always think of it like missiles. I think of two missiles, and you want one missile to intercept the other missile. Okay, so and these kind of defense systems are fairly common, right, in countries. But in order for that to happen, the two missiles have to intersect. The two missiles they're traveling along two space curves, and the two missiles intersect. Well, for the missiles to intersect, that means at some point the x coordinates and the y coordinates and the z coordinates of the missiles have to be the same. They have to be the same. So, does that make sense? Is that clear? Okay, Yeva's good with that. All right. All right. And Matthew's good. Okay. So So for that to happen, then you have to set the components equal to each other. You have to set the components equal to each other and see if you can find a value of T and S that satisfies the system of equations that results. So here's what we do on the next page. Here's what we do. Where these two space curves intersect, okay, where the two space curves intersect, okay, we must find values of T and S such that these three equations are true. You see how I equated the components of the two space curves? Here's one equation. Okay, those are setting the x components equal to each other. Here's the second equation, that's setting the y components equal to each other. And you have this third equation where you're setting the z components equal to each other. This is a very important applied problem. Okay, calculus 3, multivariable calculus is used a lot in engineering. I have a friend who, Dr. Carbone, who had a career as an engineer, and you know, these are very important concepts what you're learning. So in multivariable calculus. So look, we want to solve these three equations for T and S. So what do I do? What am I going to do? Well, I'm going to look at the first two equations because they're the easiest. Okay, I'm gonna look at the equations 1 and 2, and I'm going to try to solve that system of equations. So what I do here, well, notice what I'm doing here is in the second equation, I am replacing the t here with 3 minus s. Okay, I'm making a substitution. All right, I'm making a substitution. Now, let's see what happens. Okay, well, we end up getting s minus 2 equals s minus 2. This is non-informative. It's a true statement. We have to have true statements here because the curves intersect at some point. But that's not informative. I'm not going to learn anything about what value of s is or the value of t is for my space curves. So that means now I'm going to try to use, well, why don't we try to use the first and third equations? So if I use the first and third equations, again, what I'm going to do is in the first equation, I'm going to let t equals, I'm going to substitute in the second equation, the 3 minus s here, for t, and try to solve for s. So when you work this out, you end up getting s equals 2. Okay, and so since t equals 3 minus s, okay, if t is 1, that means if s is 2, okay, one moment, let me just, hold on. Okay, so if s is 2, okay, there's 2. So then this means t equals 1. So you could interpret this as like, well, all right, with respect to if these are missiles flying in space, they're both going along two paths, and perhaps after 1 minute, the first space curve will the first missile will collide into the second missile, and the second missile has been in the air for 2 minutes. You see? I mean, you can think of it like that. Are there any questions on this kind of thing? Okay, so the reason I thought this was an important problem to emphasize with you is, I mean, I don't know, I think some students might think, oh, this problem isn't going to work because the first and second equations, I didn't get anything. You know, I can't solve for S and T. Well, you didn't get like a lie. S minus 2 equals S minus 2 from the first and second equations, but you just have to use the first and third equations. So now the point of intersection is going to be 1, 0, and 4. So, like for instance, how do we get that? Well, R of 1, if t is 1, that would be 1, 1 minus 1, and 3 plus 1 squared. So that's 1, 0, 4. If you had, you know, S equals 2 in the second space curve, the second vector equation, you'd have 3 minus 2. 2 minus 2 is the second component, and then 2 squared is the third. And that's also going to give you 1, 0, and 4. So that is your point of intersection. Are there any questions so far before I move to the next page? All right, well, now they asked, we want to find the angle of intersection correct to the nearest degree. So the two missiles collide, okay, and there is an angle of intersection. How do we find angles? What properties have we used in order to find angles? The dot product. That's right, Yeva. That's right, Lexi. So we're going to utilize the dot product here. But dot products are used for vectors, right? They're used with vectors. So look at what we do here. Look at what we do. Here's a picture where I've drawn the two space curves. I can probably color them just to add a little pizzazz here. Okay, there's the first space curve. Maybe I can. There's the first space curve. Let me try this again. Okay. And then the second space curve, I'll make it in blue. And here's the point of intersection right here at 104. And okay, this here is the angle theta that we're looking for. Okay, that's the same as like this angle here, right? So we can get the angle theta by finding the tangent vectors to these space curves at the point 104. and then we utilize the dot product. I mean, it's quite fascinating, really. You think this will make a good exam problem? What do you think for your exam next Friday, second exam? Everybody's kind of quiet. All right. All right, Christopher likes it. Alexander's, he's smiling, but he doesn't know for sure. Okay. Norina likes it. All right. Mary likes it. Wonderful, wonderful. Well, so I have the vectors here, R1 of t and R2 of s. Okay, and I take the derivatives of those vectors. Okay, as you see here, and then I put in the values for t equals 1 and s equals 2, and those would be those are the tangent vectors that you see in our picture here, right? The two tangent vectors. Here and here. So, you know, let me just, so I think the picture is good. I think the picture is pretty good. You see the two tangent vectors, those vectors at the point 104. So now you just, you know, use the dot product formula and you'll get theta equals 54.7 degrees. Did anybody have a little trouble with this one in the homework? Did this one give anybody a little trouble? Or was it, okay, yeah, all right, very good. And okay, wonderful. And Mary's comfortable now with it? Good, excellent, excellent. Okay, let me give you a moment to finish copying that. All right, and what we're going to do now, we are going to continue talking about section 10.2 just a little bit more, because we have to talk about integration. We have to talk about integrals. So you learned about derivatives of vector functions. What about integrals of vector functions? Well, let me bring up the ebook for a minute. Give me just one moment. Okay, let me get it off of here. Okay, let me see here where we're at. Yeah, this is what we want. Let's see. Okay, so the definite integral of a continuous vector function can be defined in much the same way as for real valued functions, except the integral is a vector. Okay, and just like when you took the derivative of a vector function, you found that derivative vector by taking or the tangent vector, you found that by taking the derivatives of the components of the vector. Well, for the integral of a vector, the way that works is sort of natural. You just take the integrals of the components. So if you want the integral of a vector, you just take the integral of the components of the vector. Okay. And this is very helpful. Okay, very helpful, because like if you have an acceleration vector, okay, like section 10.4 talks about acceleration vectors. Well, if you want to get the velocity vector, you would integrate the acceleration vector to get the velocity vector, right? How many remember that the antiderivative of acceleration is velocity? Yeah, absolutely. And let me ask you this. That's right, Ava. That's right, Mary. That's right, Simon. And what if you if you have the velocity vector and you want the position vector, okay, what would you have to do to the velocity vector? What would you have to do? That's right, Alexander, the antiderivative. Okay, so what you're learning here, you're going to see again in section 10.4. Really, 10.4 is, I mean, a lot of what you see in 10.4 is based on what you're learning in this section. So given that, let's go ahead and look at an example here. Okay, so take a moment to copy this example down, and then we'll talk about its solution. Okay, so in this problem here, we're given a derivative vector, and also, well, we're given a derivative vector, and we want to find the position vector. So in order, and I think you know that we have to integrate the derivative vector here, r prime of t, in order to get our position vector r of t. But we have to remember that whenever we integrate, we have to, you know, when you do an integral, if it's not a definite integral, then you're going to get a constant of integration. That's also true if we integrate a vector. If we integrate a vector and we're doing like an indefinite integral of a vector, we're going to get a constant vector of integration. And so in order, which we want to solve for, if we're going to find out exactly if we want a unique value for this position vector r of t. And that's why you're given in this initial condition. At time equals 0, our position vector will have coordinates 1, 1, and 1. Okay, so let's go ahead and integrate this, this derivative vector. Okay, so here we are. Here we are. Just like the logical definition tells us, if we're going to integrate our vector, then we integrate the components of the vector, the component functions, I should say. We could also call let me see here, the t and e to t and t times e to the t, the parametric equations. Well, it's the parametric equations of this derivative vector function. But let's not get too caught up in the details. So I think you agree that these integrals are not that hard, right? So you know how to find antiderivatives. You know how to find those. So the first antiderivative is very straightforward. Second antiderivative, the antiderivative of e to the t, we know that. What's the antiderivative of e to the t? Do you remember? Good, good, Mary, good, Alexander, good, Angela, e to the t. And now this third one, we will need the antiderivative of t times e to the t. Oh, what am I using here? That's right, good, Norina, integration by parts. So integration by parts, the substitution, okay, those are going to certainly come into play in some of your homework problems. So if you let u, well, remember the formula for integration by parts. Okay, the integral of u dv equals u times v minus the integral of v du. Right? That's your formula. And I know that we let u equals t and dv equal e to the t dt, then this integral is just the integral of u dv. And then that will equal here, this is u times v minus the here, this here is just the integral of v du. Okay, so hopefully that is good. And so now we end up getting our position vector, but because all of the integrals are indefinite integrals, okay, we get this constant vector of integration. This is the constant vector of integration. So we don't get a constant of integration. That's when we integrate real valued functions. When we integrate vector functions, we get a vector, a constant vector of integration. Which makes sense because all the little constants like this, like for this third component here, you know, this third component, for instance, is t times e to the t minus e to the t plus c times the vector k, right? So like, maybe I can make this a little more clear. Hold on. I have an idea. So I'm going to put in, I'll call this C3. I'm trying to help you understand about that, about the constant vector of integration down here. Help you feel comfortable with it. So you see, if you were to multiply all this out here, your constant c would equal, the constant vector c would be c1 times I plus c2 times j plus c3 times k. Do you see that? That would be the constant vector c here. Does that make good sense to you? How are we feeling with that? Are you seeing that? Good. Yeva's seeing it. Angela's seeing it. Okay. Good, Norina. Good, Simon. Excellent. Excellent. So you see, rather than I could write, excellent, Matthew. Excellent, Abdullah. Excellent. I mean, I could write this, but it's much easier just to write a constant vector c. Notice I have the vector symbol above. Okay, this is why it's important to use good notation. Now what we need to do is we need to find the value for that constant vector. Well, let's remember that we were given an initial condition. We were told that, hold on here, we were told that at time equals 0, our vector function r is equal to I plus j plus k. So I can substitute in 0 for t, okay, into my vector function r, and by doing that, I'm able to actually then show that the constant vector c is equal to the vector I plus 2k. Or you could think of it as I plus 0j plus 2k if you wanted. Take a moment to look at that. Okay, and so now, okay, we can rewrite the vector r of t this way. I mean, we know that the constant vector c is I plus 2k, but then you can combine like terms, right? You can combine like terms and just rewrite the vector as you see here. So actually quite beautiful, this idea. Are there any questions on that particular example? Okay, who's feeling good? Who's feeling good? Who's feeling comfortable with integration? Yeva's comfortable. Okay, Angela's good, wonderful. Norina, wonderful. Christopher, Matthew, Aura, wonderful, wonderful. Okay, well, what I'm going to do, I'm going to give you 10 minutes of time here. Alexander, very good. I'm going to open up the section 10.2 assignment that's due tomorrow. And we have a lot to cover tonight. Let me go ahead and open up section 10.2. It should be, if you refresh your WebAssign screen, is it visible? Okay, wonderful. So let me give you 10 minutes to work on that. And then we will continue, maybe you can get one of those questions, right? Get a little head start on your homework. And then we will continue on into section 10.3. So I will see you in 10 minutes, about 6:57. Okay. Let me see. One moment. Yes. Yes, Lexi. I see you're ready for that one. One moment. Let me do that. Okay. See you in 10 minutes, everybody. All right. Excellent. And we're done with section 10.2.